Thank you, Jose and Anne, for the kind invitation. It's my great pleasure to be back here in this beautiful summer. I'm going to talk about the aggregation-diffusion equation. So first of all, let me talk about what my lectures will not have. Okay, unfortunately, it will not be having much about the biological modeling. So I consider myself as analyst. So it will be mainly about just analysis of this equation, and also even though this equation can be derived from interacting particle systems, I will leave that to other experts. So throughout the time, I will just be considering it as a continuum PDE. Okay, so to begin with, let me introduce so aggregation-diffusion equation is actually a family of equation, and I will start with the one that is the most well-studied, which is the Kähler-Segal equation in the family. So in this talk, I will be aiming the talk at the students who do not know much of the equation before. I know that quite a lot of you in the audience are already experts on this equation, and for those people, please bear with me. Well, I guarantee that you won't learn anything from my talk today, but well, maybe you can find something more interesting to do. So the Kähler-Segal equation was derived independently by Patlak and Kähler-Segal, and it has been extensively studied for more than half a century. So it models the collective motion of cells. The bacteria are called E. coli, and or slime mold also have a similar behavior. So they are attracted by a chemical substance that is emitted by themselves. Okay, so for those students who do not know how this equation is derived, I would like to show a quick derivation because when I was looking at this equation first time as a student, I found it quite scary. So what is this non-local convolution thing about? Right, so but the reasoning is actually as follows. So rho is the density of the bacteria, and we assume that, so this is the derivation. So for the rho equation, it's common to assume that, well, the cells are doing Brownian motion by itself, and then if this is the only thing that they do, then on the continuum level, their population density is well known to satisfy the heat equation, right? And in addition to doing Brownian motion, what they also do is that the cells, they like some chemical concentration, chemical substance. So C is the density of chemical substance. Okay, so then there is an additional drift term that is pointing in the direction of gradient C, where this chemical substance gradient is increasing the fastest. Okay, so this equation itself is still a linear equation in rho, right? And if C is a given function, then this would be called the Fokker-Planck equation. But what makes this system interesting is that C is not an a priori given function because this chemical substance that the bacteria like so much is actually produced by themselves. So C satisfies the following equation. On the one hand, it is also diffusing, and on the other hand, it is actually produced by rho. Okay, so this is what links them together. And now you may say that, well, but this looks like a system of parabolic equation. It has nothing to look like that single equation. Well, this system itself is called the parabolic Kähler-Segal system. People often do the following simplification. So they notice that these two phenomena, the movement of the bacteria and the evolution of this chemical density, they don't quite happen at the same time scale. So in the sense that the chemical substance actually reach its equilibrium at the time scale that is much shorter than the movement of the bacteria. Okay, so for this reason, it's common to multiply a tiny constant epsilon in front of the time derivative of C, indicating that the second process is happening at much faster. And people often take the limit as epsilon goes to 0, so that so this system now is called the parabolic elliptic Kähler-Segal equation. Okay, and now you may say that, well, but how is this connected to that? So once we are having the second equation, it allows us to solve for C in terms of rho at any moment, right? So in this case, C is given by the negative Newtonian potential convolved with rho. And the Newtonian potential would be depending on the dimension of the problem. So traditionally, this problem is set up in R2 because the bacteria are living in a two-dimensional Petri dish. And if we are in R2, the Newtonian potential would be the 1/2 pi log x. Okay, and then once we solve for C in terms of rho, plugging this in, this is where you see the convolution in the equation. Okay, so I want to point out that there are also a lot of variations in this system. So for example, one possibility is to, in the second equation, to also include the decay of C, right? So in this case, it could be Laplace C minus some constant times C plus rho. Right? So even if the decay is involved, C can also be solved as a certain convolution of rho, right? But that won't be Newtonian potential instead, it will be Bessel potential. So for a lot of analysis that I will be talking about, the exact formula of the potential is not important. So for example, for a lot of the well-postness theory, it's mainly concerned about like whether the equation can blow up. It's mostly depending on how singular this potential is at the origin. And in that sense, the Newtonian potential and the Bessel potential have the same type of singularity at the origin. It's only the tail behavior is different. In the later result that I'm going to be talking about, the exact formula of the potential doesn't matter that much, but throughout this talk, I'm going to assume that the potential is always an attracting potential, which means that it is always a radially symmetric function, and it is an increasing function in the radial direction. Okay, so that is the derivation of the equation. So math-wise, this equation has a very fascinating phenomena that is the so-called critical mass phenomena. So the mass here is just the integral of rho. Let's call it m. And so this is actually a conserved quantity in time because because of the divergence structure of this equation, if you take the time derivative of this quantity, you will easily see that it is equal to 0. So mass is conserved in time. And so it turns out that depending on the size of the mass, so the solution can either have a blow up in finite time, or it can dissipate to infinity, or have some infinite in time growth phenomena. So the very fascinating result is that, well, for all the initial data with finite second moment, as long as the mass is bigger than 8 pi, then all the solution must blow up. Okay, so for those students who haven't seen this proof before, I consider it as a very nice, short, and cute proof, and I would like to show it to you because it's by a very nice proof by contradiction argument. Okay, so the proof of blow up for mass bigger than 8 pi. And again, for the expert in the audience, please bear with me. So the proof goes the following way. Let's define the second moment as rho times the absolute value of x squared dx. Okay, and then we are going to track how this quantity evolve in time. So let's take the time derivative, assuming that there is a smooth solution in time, and then we have the second derivative, have time derivative that is, well, I'm supposed to replace this rho by rho t, right? And therefore, there will be two terms coming in. One is the Laplace rho. So for the Laplace rho term, we can do the integration by parts to move the Laplacian to the x squared, right? And that term, because we are in 2D, it will be a constant, so that constant is equal to 4. right? So this term is just the integral of 4 rho, which is 4 times the mass itself. Right? So that is the contribution from the diffusion term. And the contribution from this aggregation term, let's also do this computation. So I'm first going to do the, to write down so this is the divergence term here, right? So I'm going to be also applying the divergence theorem to move this divergence onto this x squared term. So that is going to give me the plus will be becoming a minus, and then I will have an integral of rho gradient Newtonian convolved with rho, and then times 2.2x dx, like this, right? So this term, if it is written in this way, it is hard to see what it is, right? So the clever observation is that, well, we can write this as a double integral, as rho of x, rho of y, therefore explicitly writing out the convolution. Okay, and then when writing out the convolution for the gradient, I have the option to let it hit either n or rho, so I'm going to let the gradient hit n. Okay, so this term is going to be a double integral of rho of x, rho of y, and then the Newtonian potential is 1 over 2 pi x minus y squared. Right, so that is the Newtonian potential, and then dotted with 2x dx dy. Right. So by rewritten it as a double integral, I'm going to play the trick that is a common trick. So if I switch x and y, the double integral will not change, right? And then, so if I switch x and y, this rho part will remain the same because rho y, rho x is the same. And meanwhile, if I switch x and y and also average it with the original integral, then I will have the following thing. So I used to have an x squared, if I pull out the 2 here, I used to have an x squared minus x dot y. Right? And then if I exchange x and y and then symmetrize it with the original one, I will have a further y squared minus x dot y. Right? And this is exactly the same as the denominator. Right? So, and then the 2 will be going away because I am taking the average of the original integral with the switched version. So that's how the 2 goes away. But the 1 over 2 pi, the constant is still sitting here. Right? So then you see that this double integral is actually just 1 over 2 pi times the double integral of rho x, rho y, dx, dy. Right? So this term goes away. So it means that it can be written as 4 times the mass minus 1 over 2 pi times the mass squared, right? So this is a very nice observation because it says that the second moment actually evolves according to this very simple rule, right? Mass is the constant over time, so we have, in particular, this is equal to, if we pull out a 4m, it's easier for us to see the sign. So this is exactly 1 over m over 8 pi, right? So if m is bigger than 8 pi, this will be a negative constant. And you may ask, well, what is wrong with that? Well, the contradiction goes in the way that if m is bigger than 8 pi, then the time derivative will be a negative constant. And therefore, if we are tracking how the second moment is evolving in time, it's going to start with something that is initially finite, and then it's going to drop linearly, right? But meanwhile, from its definition, we know that, well, it's the integral of rho times x squared dx. We assume that rho is initially a non-negative density, and the non-negativity is preserved in time. So it means that the second moment, as long as we are having a classical solution, should always be positive, right? So then if we call this time to be capital T, then the conclusion is that there cannot be a classical solution going past this time, right? So the solution can't exist past time t. Right. So this is the very nice proof. So I learned it from the Blanchet, Daubot, and Pertham paper. So that is the proof for the blow-up for m is bigger than 8 pi. And when m is less than or equal to 8 pi, the solution actually is the global in time. So let me also mention a little bit about the global existence proof. In this case, we cannot just track the evolution of the second moment, right? Because there is no contradiction, but it doesn't say that the solution will be globally bounded. So here, the global well-postedness proof actually is using the logarithm Hardy-Littlewood Sobolev inequality. So in this case, it turns out this equation has an associated energy functional. And this energy functional will be appearing throughout the whole talk. For the linear diffusion, it is rho log rho. And if we are replacing the linear diffusion to nonlinear diffusion, it becomes something else. And plus 1/2 of rho times. So this is what the associated energy functional look like. Okay, so the reason for such functional is because if we force ourselves to write the whole equation into one single equation that is like a transport equation, divergence of rho times something. Okay, so this something is the velocity field that rho is being transported. If we force ourselves to write it in this form, then it will be written as gradient. So the linear diffusion term can be broken into the divergence of rho times gradient log rho. And the rest of the term just happily sits here. Okay, and it turns out this term is the first variation of such energy functional in terms of rho. Okay, so once you realize this connection, then you can easily check that as you take the time derivative of this energy functional E, it can be written as the following. It can be written as negative. So for any function that is of the form rho t is equal to divergence of rho times the gradient of the first variation, as you are taking the time derivative of E, so a simple computation gets us that the time derivative will be dE dt is equal to negative rho times exactly the gradient of log rho plus Newtonian times rho squared dx. And this part is exactly, again, the first variation. Okay, so it means that the energy functional is non-increasing in time, right? And in particular, we are having that E at any later time t is less than E of rho 0. Right? Okay, so now the global well-postedness proof is by combining this observation with the following logs Hardy-Littlewood Sobolev inequality. So it says that for any density function, non-negative density function, if rho has mass m, then the following inequality holds. So the integral of rho log rho plus 4 pi over m times rho of the, so here I am directly writing the 1/2 pi log as a Newtonian so that it's easier to compare it with the energy functional. And the 2D Newtonian, the log function convolved with rho dx. So the sum here is bounded below. Okay, so the right-hand side constant will be something that is depending on the mass m, but for any non-negative function rho, so this holds. Okay, so this is finite. Okay, and then how can this inequality be used to show the bound of rho in the evolution? Well, the key is that if we are comparing this E of rho with this left-hand side, we can write it as the following. So we have, on the one hand, we have already discussed that, well, the initial energy is bigger than the energy at a time t, right? And then I'm going to break this energy at time t into something that looks like this plus something else. Okay, so namely, I'm first going to do m over 8 pi so that this and that would cancel out, right? This part would be taking care of the coefficient 2 pi of the integral of rho log rho plus 4 pi m rho. Oh, right, larger. Okay. Okay, so I'm going to have this term right here so that these two coefficients is going to produce the right coefficient 1/2 in my energy functional, right? But then this is not an inequality yet because I am supposed to have the rho log rho with coefficient 1, but now it has coefficient m over 8 pi, right? So I need to add a 1 minus m over 8 pi times the entropy part, like this. Right? Okay. So then what we have is that, well, by broken this energy E into these two parts, for the first term here, by the log HLS inequality, we know that this term is bounded below. Right? And for that reason, so this bound below can help us to figure out that, well, this term will be bounded above. Right? And now, so this is again where the mass less than 8 pi is going to come into place, right? So we know that this is a positive coefficient. So this coefficient times the integral of rho log rho being bounded above implies that the integral of rho log rho is bounded above. So this is uniformly bounded above in time. Right? The bound will be depending on the initial energy, and it will also be depending on the mass. Right? Okay. And then it's not the end of the story yet. So let me just briefly mention the step next. So once we have the integral of rho log rho is bounded above, it turns out it's not too difficult to add an absolute value here. Okay, because log itself may be negative or positive, right? But it turns out that under the additional assumption that the second moment is also bounded above, so the parts that the log is negative cannot contribute too much. So one can, combining it with the second moment, one can upgrade it into this, into an absolute value here. And this is giving us some uniform integrability of this quantity, right? So it means that, well, we know that such kind of rho cannot be concentrating into a delta function, right? So this control is weaker than all the uniform LP bound, but at least it excludes that rho being too concentrated. And once we get this, you can run a rather standard energy argument to further say that, well, once this quantity, we have this a priori bound, then you can improve it into any LP norm of rho being uniformly bounded, L infinity norm, and then because this is the parabolic equation, so having these LP and L infinity norm being bounded in time actually implies that there is also the regularity that is uniformly in time. Okay, so for m less than 8 pi, so for this proof, you can check this uniform bound part for rho log rho in the later two paper, Dobol per thumb and Blanchet Dobol per thumb, and then earlier in the Jigger and Lukehouse paper, it is already known that this quantity, if we know this is uniformly bounded in time, then the solution will remain regular. Okay, so and actually, not only we know that solution will be bounded globally in time, but people also know that, well, as time goes to infinity, it will be converging to, so it will be spreading like the heat equation scaling, and in the rescaled variable, it will converge to this self-similar solution with the heat equation scaling. Okay, so that is the story for m less than 8 pi. For m equal to 8 pi, it's also known that there won't be a finite time blow-up, but the solutions with initially bounded second moment, all of them will be having an infinite time blow-up, which means that their L infinity norm will be growing with certain rate as t goes to infinity. And for those whose initial second moment is infinite, some of them, if they are initially already close to a steady state, by the way, in this case, as m equal to 8 pi, there is a continuum family of steady state. They are of the form 1 over 1 plus x squared. Sorry, I may be missing some of the constants here, but they all look like this. Or the scaled version of them. So this whole family has mass 8 pi. All of them have infinite second moment. Okay, so there are also stability results saying that if you are initially close to one of them in some sense, then it will be converging to them as time goes to infinity. So that is a story for the Keller-Segal equation itself. Yes?
It's for the case where m is greater than 8p.
Yeah.
So the time t that you, is it the...
So this is just a proof by contradiction, right? All we have from this proof is that there is no way that we can have a classical solution up to this time, right? But the actual blow-up time may happen sometime early, right? That is a possibility. Yes, sorry, I should have said more. So this is just a quick proof of the, like, there can be a classical solution, but the actual study goes way more than that. So up to this moment, it is well known that, so at the time of blow up, there must be a delta function concentration, and the delta function needs to have mass at least 8 pi. So that is known. And also, the structure of the blow-up is also studied. So you can see the paper Collot, Gao, Masmoudi, and Nguyen. So that paper mentions that, well, so they have classified that there exists this, it's not exactly a self-similar blow-up. So there is the main part of mass 8 pi. And then, and then as the time goes to the blow of time, it will be concentrating to a delta function. And the blow up is not exactly a power law. It is a power law with a log corrector. So the details of that log corrector and the details of this, the blow up rate and the profile, these are all extensively studied. Yeah, thank you, very nice question. So that is the story of the Keller-Segal equation with linear diffusion. And in my talk, I'm going to talk about a generalized version of this model. So first of all, I'm going to replace the linear diffusion with a possibly, it could also be linear, but also possibly degenerate diffusion. Okay, so here I'm going to assume that m is bigger than or equal to 1. So the biological motivation come from the paper by Boy, Capasso-Morale, and Topaz, Bertozzi, and Lewis. So a power m bigger than 1 is modeling the anti-overcrowding effect. It means that the bacteria are not just doing Brownian motion. If that is happening, then it will correspond to the linear diffusion. But they actually have the tendency to avoid being too crowded. Okay, so the diffusion rate is actually higher as the density gets higher. So that's where the extra power comes from. Right. So intuitively, we can see that this term, the bigger the m is, the stronger it's going to prevent blow up, because the larger m would mean that, well, if the solution is trying to concentrate, then the larger the m is, the stronger the diffusion would be, right, at that point. So intuitively, m bigger than 1 should make us easier if we want to prove global well-posedness. And also, so in the previous Keller-Segal equation, I said that the interaction potential can be Newtonian potential, it can be Bessel potential, depending on what is the assumption of the modeling. Right? So here, I'm not going to assume that W is any particular formula, but instead, we are going to assume that W is just any attractive potential, which means that so it is radially symmetric and increasing. So W could look like this, like the log potential, or it could also look like something like this, right? So so there may or may not be a singularity at the origin. There may or may not be growth at infinity. So either way is okay, as long as W is radially increasing. Okay, so this means that if we think about the second term as a pair of two particles and they are interacting in each other, so any radially increasing W will correspond to that. For any pair of the particle, they are mutually attractive. Okay, so if the monotonicity of W is the other way, then they would be repulsive instead. So there is also the interest to study the potentials that are repulsive in short range, attractive in long range, but these potentials will lead to quite different results, and I will be talking about that later. So for all of our results, we are going to assume that W is a radially increasing potential. Okay, so now for this equation, the global well-posedness versus the blow-up criteria has been well studied. So namely, for any interaction potential W, depending on how singular it is near the origin, there will be a critical power m such that when m is bigger than this critical power, it leads to global existence of the solution. And when m is less than this power, there could be a finite time blow up. Okay, and in particular, if W is equal to n, then m is equal to 2 minus 2 over d. Here, d is the dimension. That is the critical power. And then one can do a sanity check that, well, if d is equal to 1, then the Newtonian potential exactly have the critical power 1. Right? It means the Keller-Segal equation that we were talking about is exactly the case when the diffusion power is critical. Right? So in the next slide, I will show you that how this critical power can be figured out in using a heuristic argument. But the focus of this talk is not going to be the well-posedness. It's more about the steady state and the long-time behavior of the solution in the regime where we know the global well-posedness. Okay. So now let me show you how to formally figure out what should be the critical power. Okay, and also to introduce to you the main tool that we are going to use for the analysis. So just like the Keller-Segal equation, for the aggregation-diffusion equation, there is also an associated free energy functional, which looks like the following. And from the structure of the functional, you can also see that it has two terms. One term is coming from the degenerate diffusion term. The other term is coming from the non-local aggregation term. And it turns out that these two terms will be competing with each other, as we will see very soon. Okay, so the derivation of this functional is the same as, has a similar flavor as here. So now we are having this degenerate diffusion equation. If m is equal to 1, then it's exactly the same as this part, right? So if m is bigger than 1, then if we force ourselves to write the equation into one single transport equation, we can do that, and then the rest of the term will look like m over m minus 1 rho to the power m minus 1 plus now the potential W convolved with rho. Okay, and again, if we play the same trick, we ask ourselves that, well, what is this term here? Then we will see that, well, this term turns out to be the first variation of the energy functional if the energy functional is defined by that. Okay, and then through the same computation like that, so if we formally take the time derivative of the energy functional, we can see that the time derivative is non-positive. Right? So it means that the functional is a Lyapunov functional along which along a solution the functional is dropping, right? And actually it is more than a Lyapunov functional, in the sense that the solution can actually be written as a formal gradient flow of this energy functional. So it means that at each time, so your solution is evolving in the direction where this energy functional is dropping the fastest. Okay, so when I say the gradient flow, I need to define two things. Of course, one is what is the functional that I already have shown you. The other one is, well, what space am I using, right? What is the metric space? And here, the metric space is the space that is endowed by the two Wasserstein distance. So I believe that there will be more lectures in this summer school about the Wasserstein gradient flow. So I won't be talking too much about it, but more details can be found in the book by Villani on the topics in optimal transport, and also in the book by Ambrosio, Gigli, and Savary on gradient flows in metric spaces. So why do I add the word formally? It is because to rigorous make this gradient flow work, one needs to know some convexity of this energy functional along the geodesics. Okay, so for all the m that is bigger than or equal to 1, this entropy term is convex along the geodesics, but the interaction energy may or may not have the sufficient convexity depending on what is the potential W. So if the potential W is convex, then it is well known that this term is also convex along the geodesics. Or if W is just semi-convex, that is also sufficient to establish this rigorous gradient flow formulation. Okay, but if W has a singularity near the origin, then we see that, well, near the origin, there is no convexity or semi-convexity at all, right, for this potential. So that is theoretically an issue to rigorously justify the gradient flow formulation. In some cases, under certain assumption, one can still make it work. So for example, Katie Craig, she shows that when W is the 2D Newtonian potential, then if we are looking at the geodesics along these densities whose L infinity norm is bounded, then the interaction potential, the interaction energy term is still it's slightly worse than semi-convex, but it's just by a logarithm worse than that. But the well-postedness of the gradient flow can still work. But for W that are even more singular than the Newtonian, I don't think there are any theories for the formal, for the justification of the gradient flow yet. Okay, so that is the energy functional. And now I would like to show you, using this energy functional, how to formally see what is the critical power for well-postedness versus finite time blow-up. Okay, so the argument is a scaling argument. So I will be showing it to you for the Newtonian potential as just an example, but it can be applied to any potential as long as you know that near the origin what kind of singularity power law it is. Okay, so the idea is as follows. Starting from this energy functional, let's try to plug in the density into the E of rho. So the density that we're going to plug in is, well, rho is just any density that you initially choose. Okay, and then we are going to scale it into this rho lambda. So rho lambda is going to be scaled such that it has the same mass as rho, but it's just dilated in some way. Right, so this is rho, and we are going to, so rho lambda for lambda bigger than 1 is going to be making it more concentrated. Right? And you can see that as lambda goes to infinity, basically we are making a delta function with the same mass as rho. Right? And now I'm going to plug in this rho lambda into the energy functional E and to see that, well, what kind of power of lambda is popping out in these two terms. Right? So the intuition is that, well, because along a solution, we know that the energy functional is decreasing. Right? So now if we are plugging in a very concentrated version of rho into the energy functional E, we want to see that, well, is that making the energy functional to be positive infinity or negative infinity? Right? So if the energy is going to be minus infinity as we are plugging in this super concentrated version of rho, then it means that it seems possible that a blow-up can happen, right? Because the energy actually decays to minus infinity as rho gets very concentrated. So let's see what's the power that pops out. If we plug in rho lambda into E, then the entropy term will be carrying the power lambda to the m minus 1 times d. And for the Newtonian potential power, one can check that it will also be a power of lambda popping out, but it will be lambda times d minus 2. Right? So in this case, let's see which power becomes stronger as lambda goes to infinity. Right? So it depends on how does the two power m minus 1 times d versus d minus 2, how they compare to each other. And when m is equal to 2 minus 2 over d, this is exactly the power that they balance each other. Right? So if m is equal to this power, then it means that when you are plugging in rho lambda into E, then there are no terms that are stronger than the other. Right? So this is called the fair competition case. And in particular, when d is equal to 2, we see that the Keller-Segal equation is satisfy this. Right? So when m is bigger than this power, then the power in front of the entropy term would win. So it means that it is not energy favorable to make it super concentrated, because making it very concentrated will actually be making the energy into infinity. Right? But if m is less than this power, then this is called the aggregation-dominated case, because it is actually, it is really energy favorable to make it very concentrated. Okay, so this is just a formal way to figure out the power, and it is not a proof of global well-posedness versus blow up, right? Usually what people do is that you first run this formal argument to figure out the power, and then when it comes to the actual proof, the global well-posedness proof will be done by something, it will not be done by the log hardly-lived Sobolev inequality, but just the regular HLS inequality. Okay, so using the usual HLS inequality, one can get an a priori bound. So using an argument similar to that, one can get so at the critical power, one can so first of all, for the diffusion-dominated case, one can show that the solution exists globally in time, and also the L infinity norm stays uniformly bounded in time. Okay, so it means that this is the regime where there will be no blow up, but as I will discuss that the long time behavior of the solution remain unclear in many cases. Okay, so that is the main regime that I'm going to talk about. And when m is less than this power, it is known that for any mass that is bigger than 0, regardless of how small it is the mass, so there exists solution that blow up in finite time. However, if the solution has sufficiently small initial data, here the sufficiently small is in the sense of some higher LP norms, then the solution will be global and it will be dissipating with the porous medium equation scaling. Okay, so such result is discussed by this paper. And by the way, the Chen-Liu Wang paper, the Chen is Li Chen from Mannheim, and she's also here. So that is this aggregation-dominated regime. And now if we come back to the critical regime, this fair competition case, then it is more complicated because it's like the Keller-Segal equation with linear diffusion. Again, at this critical power, there will be a critical mass, and that will be separating the global well-posedness versus finite time blow-up. Okay, so more precisely, if the mass is less than the critical mass, then, and by the way, this critical mass will be arising from the optimal constant of the Hardy-Littlewood-Sobolev inequality. Okay, so if the mass is less than the critical mass, then the things are more well studied. It's known that the solution will be bounded globally in time, and just like the Keller-Segal equation with subcritical mass, they will be dissipating as time goes to infinity, except that they will not be dissipating with the heat equation scaling, but they will be dissipating with the porous medium scaling instead. Okay, so things are quite well understood in this case. And if the mass is bigger than the critical mass, Bedrosian and Kim showed that all the radially symmetric solution will blow up in finite time. Okay. However, there is still an open question that is, so for non-radial solution, it is known that, well, if they are initially very concentrated and has the initial free energy functional to be sufficiently negative, then they will blow up. So that is known. However, to the best of my knowledge, it's still an open question that, well, if you just give me an arbitrary non-radial initial data, then does that initial data necessarily lead to a finite time blow up? Okay. And if the mass is equal to the critical mass, in this case, there will also be a family of steady states. They are all scalings of each other. But unlike the m equal to 1 case, where all the steady states will have a big tail, so when m is bigger than 1, all of them will be compactly supported. Okay, so and they will also all be scalings of each other, carrying the same mass, and so it's known that all the radially symmetric solution with compact support will be converging to one of them in this family as time goes to infinity. But again, so to the best of my knowledge, for non-radial solutions, the dynamics is still unclear. Okay, so that is the story for global well-posedness, blow-up, and long-time behavior of what is known in the literature. So for my talk, we are trying to understand the diffusion-dominated regime where there is no blow-up, and we would like to understand the long-time dynamics. Okay, so first of all, before I get to these results, so I think this is the time that I pause for just, so for the literature review part or the derivation of any of these results, is there any questions from the audience? Yes?
No, I just want to ask some remarks.
Yeah.
Concerning this critical case for the M.
Yeah.
Actually, in 2014, with James 1, we had a result. Like, if the M is smaller than that one, this MC, proposed, but bigger than the one that from the, how do you call it? The another.
Oh, right.
Exponent, then we propose a critical criteria for the initial data that you can get either global existence or finite time. That's some hidden.
Oh yeah, right. I remember your result now. So it's about so what I am doing here is like the mass critical scaling, right? But then one can do the other scaling with the solutions with finite infinite mass, right? I guess your family of solution will.
Exactly, that's a different criteria, but somehow in some region of the M, it's clear whether the solution exists or blow up.
Right.
But it's nothing to do with the mass.
Yeah, right. Yeah, so then in that case, your critical power, I remember, is not 2 minus 2 over d, but it's something else, right? Also,
2d divided by d plus 2.
Yeah, thank you for the comment.
Just one remark.
Yeah, right. So for that scaling, you can check Lee's paper for that. For the whole talk, I'm going to focus on the case with finite mass, and in that case, it is this like mass critical scaling that applies. Yes.
Sorry, I didn't understand the discussion. So the boot M is not 2 minus 2 over d, it's 2d over d plus 2?
It depends on what assumption you are making, right? So for example, like when the way that I derive this scaling is that I start with the row whose mass is finite, right? And then I do the scaling where the mass is preserved, and then I plug it into the equation. So if that is the scaling that you do, so it means that if your initial condition, if you are going to work with the solution in L1, where you know they have finite mass, then 2 minus 2 over d would be the critical power. So what Lee mentions is that if you are starting with the solution's initial condition that with the heavy tails, right, where they have infinite mass, but you know that they belong to some other LP spaces, right? I forgot what is that P. And then you consider that family of solution, the critical power may be a different one, right? Yes?
For the aggregation-dominated version, so is there any like criteria which leads to the like finite flow up of the solution? I mean, because for the mass critical case, you give a very like sharp criteria.
Yeah, right.
But for the aggregation dominant case, you say that like there exists solutions
right.
which forms the finite time blow up, but any like concrete?
Yeah, that is a great point. So in this case, it's like really sharp, right? So for all the mass that is bigger than this, you have to blow up. You have no choice. But in the aggregation-dominated regime, the result actually doesn't work like this. So for example, here it's So you can understand it as if your initial data is sufficiently concentrated in certain norm, then it leads to a blow up. But meanwhile, even your mass is huge, if your initial data is very spread it out, then there can be global well-posedness. Right? It's like this is also reflected in Lee's result, right? So even if you are having infinite mass, right? If your certain LP norm is sufficiently small, then there can still be global well-posedness. So in that sense, I think there are criteria in terms of certain LP norms, how big or how small it is, and also in terms of some other functional. But I don't think there has been like a sharp criteria saying that above this line you blow up above. Yeah.
I can just add one comment on that. There is a paper of Correa Sampertan, in which, for instance, in the case of the Newtonian potential, dimension larger or equal than 3, that is a particular case, then the right space is LD over 2 to do these computations. But they don't have a sharp right?
Right. So it can be right. So there can be like a certain norm, but I think it's still the result are of the form that if this norm is bigger than a certain constant, there will be blow up. Smaller than a certain constant, there will be global well-posedness. But these two are different constants, right? Okay, if there are no other questions, then I think I can move on to the main question that we would like to answer in the diffusion-dominated regime. Okay, so for simplicity, you can think of the potential as the Newtonian potential and the power to be bigger than 2 minus 2 over d, even though, so a lot of these results can work with for a general radially increasing potential in the regime where we know there is global well-posedness. Okay, so in this case, all we know is that, well, there is no blow up. There is a uniform L infinity bound in time, but as time goes to infinity, this can mean a lot of different things, right? So maybe the solution will be converging to a steady state as time goes to infinity, or maybe the solution can just spread out as time goes to infinity. So we want to know that, well, which is the case, or maybe it can be something else. And to understand the long-time dynamics, a key step is that we need to first know what are the steady states, right? Because each of the steady state itself is clearly a possible candidate for the long-time behavior, right? So we think that, well, before we go to the dynamics, maybe we should first ask ourselves the following question regarding the steady state. So first of all, for a given mass, and again, I'm going to talk about the case where we start the initial data with a finite mass, right? So as Lee mentions that if the mass is infinite, then the theory will be quite different. So for a given finite mass, does there exist a steady state? And that question already has a satisfactory answer. So the idea is also to use the energy functional. Okay, so for a given mass, we already know that, well, this energy functional is dropping, and therefore it makes sense to ask that, well, whether there exists a global minimizer within this family of densities with the same mass. Right? Because if there is a global minimizer of the energy functional, then clearly this global minimizer will have to be a steady state for free. Right? Because you already start there, and then you know that, well, the energy functional is also dropping, but it can't go anywhere else. You are already at the global minimizer, so you have to be a steady state for free. Right, so so for all the existence of steady state, mostly these results are established by looking for a global minimizer of this energy functional. So this can be obtained by a concentration compactness argument that originated in the 80s by Lyons. And also Bedrosian, Carrillo, Delgadino, and Patacchini, they make it work. So Lyons' original argument deals with the Newtonian potential in dimension 3, not because he cared about its application in biology, but it's because for this energy functional that that with this degenerate diffusion plus a Newtonian aggregation. So this functional also arises in a physical model that models the formation of stars, okay? Because the Newtonian potential is also the gravitational potential. So that's what motivated his study. And he proved that when the power is above 2 minus 2 over d for the Newtonian potential, there is a global minimizer. Okay, and Bedrosian proved this for any attractive potential. If m is bigger than 2, there exists a global minimizer. And Carrillo, Delgadino, and Patacchini further refined this result for a broader class of attractive potentials. So now, so for question 1, in the regime that we are interested in, we already know that there exists a steady state that is the global minimizer. Okay, and once we know that there is a global minimizer, one can use Riesz rearrangement inequality to say that the global minimizer has to be a radially symmetric function and it is decreasing in the radial direction. Okay, so for those of you who are not familiar with the rearrangement inequality, let's say that suppose we start with the density rho, and then we are going to do the radially decreasing rearrangement. Okay, so let me just explain it using picture what it is. So you start with the density that is a non-symmetric function. Okay, with that is non-negative with finite mass, and think about it as a layered cake. Okay, so if you at each horizontal layer, if you slice your cake, the level set will have certain shape, right? So this symmetrization procedure is called radially decreasing symmetrization. It means that, well, at each layer, you are going to reshape your cake such that the level set has the same area, okay? And then you want to reshape your cake such that at each height, the level set will be a perfect disk, well, or a ball that is centered at the origin, okay? So it's like this. So in this case, from rho to rho star, such rearrangement is going to keep the area of each level set, right? And for this reason, you can clearly see that while the mass is not changing, the L infinity norm is not changing. And actually, because of the level set area doesn't change, any LP norm is remained constant in this procedure. Okay, so therefore, if we are doing this rearrangement, then the entropy term, rho to the power m, will not feel any change. Okay, but the Riesz rearrangement inequality says that for the interaction energy term, as long as W is a radially increasing potential, this term is going to, so the interaction energy is going to decrease under this rearrangement. Okay, so for that reason, the global minimizer must already be radially decreasing, because otherwise, if not, then we further rearrange it, the energy will be dropping to something even lower, and that will be a contradiction. Okay, so, so that is what is known about the global minimizer. However, this argument doesn't give us anything about the steady state that are not global minimizers. Right? So you can intuitively think about the picture as, well, so there's this energy functional, right? And our landscape consists of all the functions with the same mass, right? So the energy functional can potentially have a very complicated landscape. There is this global minimizer where we know it is radially decreasing. But meanwhile, there could be, so if on this energy landscape, there is the global minimizer, but there could also be some other critical points that are steady state, right? So you can picture this, well, you can first formally assume that, well, suppose the gradient flow formulation works, right? And then in this case, it means that all the solutions are just following the gradient flow, right? And then all the steady state, each steady state corresponds to a critical point in this energy landscape. right? So there could be some steady states that are just critical points, but not the global minimizer, right? So then our question is that, well, we want to understand what are these, right? Or if these exist at all. So in that case, we cannot use this symmetrization argument, right? Because if you directly apply symmetrization to these, then they will be going to directly the something else, right? So the energy will be dropping, but there is no contradiction, right? There could be potentially still some steady states that are non-radial. Right. Together with Jose, Sabine Hittmeyer, Bruno Bolzone, so we studied this problem for all the potentials that are no more singular than Newtonian potential. And we give a positive answer to the symmetry of the steady state. So we show that all the steady state that are non-negative, L1 and L infinity, they have to be radially decreasing up to a translation. So after our work, our condition that no more singular than Newtonian potential has been relaxed by Jose, Franka Hoffman, Eduardo Manini, and Bruno Bolzone. So the idea is as follows. So now we want to rule out the existence of all these non-radial critical points, right? So the way that we rule them out is actually based on a very naive idea that you have already learned from multivariable calculus. So let's say that you have, this energy functional, right? And then there is a critical point. So we want to show that all the critical points are radial, right? So in multivariable calculus, if you have f of x, then if you want to show that, well, a certain point cannot be a critical point, all you need to show is, well, the gradient of this is not equal to 0, right? But in this case, the gradient of a point is something that is very complicated, right? So this idea doesn't really apply. But what other thing that we can do is that, well, as long as we are able to test this point in a certain direction and show that, well, the gradient of that function at that point in this direction is not equal to 0. Okay, so it is strictly decreasing in this direction, then this point cannot be a critical point, right? So it means that we are going to try to build certain perturbation around this point, right? So we have to find a local perturbation now, instead of this directly symmetrize it to something far away, right? So standing at a point where we assume that the solution is a non-symmetric steady state, we have to find a local perturbation such that the energy functional along this direction of perturbation is dropping to the first order. Okay, so if this can be done, then we are going to argue that, well, this point is not going to be a critical point. Okay, so what is the local perturbation that we are going to construct? Well, it looks like the following, this kind of perturbation is not our invention. So in the symmetrization community, it is well known. It is called the continuous Steiner symmetrization. Okay, let me briefly introduce this to you so that in the future, if you also need to slightly symmetrize a function, then maybe you can also use this idea. So let's say that towards a contradiction, there exists this steady state, rho s, that is not symmetric to radially decreasing to begin with. Okay, so the continuous Steiner symmetrization is a procedure that can be slightly symmetrizing it. So let's say that, well, I'm drawing this 1D picture, but the proof actually works in any dimension. Okay, so suppose there is this steady state rho s that is not radially decreasing, then we must be able to find some hyperplane that is cutting the mass into half and half, and the function is not symmetric decreasing about this hyperplane, right? Okay, now let's say this is the hyperplane. Once I find this hyperplane, then we are going to look at this part under the graph of rho s. We are going to decompose this graph as the infinite collection of these one-dimensional needles that are perpendicular to this hyperplane. Okay, and for all these one-dimensional horizontal needles, we are going to mark their center of it. Okay, of course, I am drawing a simplified picture here. The actual profile may look something like this, right? So in this case, at one height, you may have two disjoint needles, and if that is the case, you mark each of their center. Okay, so because the hyperplane is splitting the mass into half and half, and it's not already symmetric about it to begin with, we know that there must be some needles whose center is to the left and some needles whose center is to the right. Okay, so this is step one. We identify the center of the needles. And the way that we are going to evolve this density is that starting from this, we are going to move the needles. Okay, so we are moving the needles such that the height and the length of the needle are kept the same, and we just move all the needles towards the hyperplane with velocity 1. Okay, so what does it mean? For example, here, this needle, its center is to the right. I'm going to move it towards the left with velocity 1. Okay, so that as we evolve it, this needle is just going to be moving in this way, right? And then here, for this needle whose center is initially to the left, we are going to move this needle towards the hyperplane who's with velocity 1 as well. Right, so now the black curve there is the initial rho s, and I'm using the red dots to denote the location of the centers initially. And if I do this procedure, if I do this needle moving procedure for a time epsilon, then I'm going to have the new centers that are denoted by the blue dots. Okay, and by the way, as I am running the procedure, as long as the needle is hitting the middle, then it's just going to stop there, right? Because it's already happy, it's already at the center. We also need to discuss the case, for example, for a situation like this, it could be possible that the two needles are hitting each other, right? So if this happens, then as long as they are touching each other, we merge them into one needle at that moment, and then we will be again finding the new center of this longer needle, and then starts the procedure at that time. Okay, so if we run this procedure for a very short time epsilon, then the new profile after time epsilon is denoted by this new blue curve, with the new centers being denoted by the blue dots. So you can see that this is the procedure that is, in some sense, making the profile to be more symmetric about the hyperplane if we run it for a short time. Right? And meanwhile, it is a local perturbation. So if we run it for a sufficiently short time, then my function is going to look sufficiently close to my initial steady state. Right? So this is rho s. So for this procedure, one thing that we know is that, well, because the height is kept the same, so if we are looking at every height, then the level set, the level set's area does not change. So the continuous Steiner symmetrization also kept the LM norm to be constant. Right? So as we are looking for the energy functional, we know that, well, there is this entropy term that is not going to change at all in this procedure. So now it's all about how the interaction energy changes. Okay, so it turns out it's already well known that the continuous Steiner symmetrization will be, so the interaction energy will be, as long as the interaction potential is radially increasing, the interaction energy will be decreasing along the continuous Steiner symmetrization. Okay, because on average, it's going to make the energy more, it's going to make the profile more symmetric. So this fact is already well known. I learned it from the textbook of analysis on leap and loss. And by the way, so that textbook contains an excellent chapter on various rearrangement inequalities. And actually, they use this continuous Steiner symmetrization to prove the Reed's rearrangement inequality. Okay, because if you are doing the continuous Steiner symmetrization in every single direction for infinitely many times, then this actually converges to that, right? So they actually use it to prove the Reed's rearrangement inequality. So the fact that E is decreasing, this thing is well known, but what we need is stronger than that. Okay, because we want to rule out, we want to say that anything that is non-radial to begin with is not a critical point, right? So we need to show that under this perturbation, not only the energy is decreasing, but it is decreasing really to the first order, right? So we need to show if we run this for a short time epsilon, then the energy is really dropping by order epsilon. Here, the constant little c in front of it is strictly positive. So this will need some messy work to figure out. So that's one of the technical part. At the end, we were able to show that the energy does decrease to the first order of epsilon, where this constant c, depending on the potential itself, and also depend on how unsymmetric the density is to begin with, in some sense. Okay, but as long as this is true, it means that if the equation has a rigorous gradient flow formulation, then we already arrive at the contradiction, right? Because we have shown that for any function rho s, this steady states that we assume there exist. There is this perturbation direction that we have found that make the energy drop to the first order, which is contradicting with the fact that it is a steady state. Right? So if that is the case, the proof would have been very clean, and we would be easily get a contradiction. Okay. Unfortunately, life is not perfect, right? We have to work with the potentials where that are too singular, too non-convex at the origin, where we don't know whether there is a rigorous gradient flow formulation, right? So this is the case where we do not. So this argument is not sufficient, right? Because all we have is that, well, there is this perturbation where the energy drops to the first order, but what? So what, right? There is no gradient flow formulation. There is no contradiction yet. So in this case, we really have to manually derive a contradiction in the sense that, well, we need to prove two things that are directly contradicting each other. Right? One thing that we want to prove is that our perturbation is dropping the energy to the first order. The other place that we want to do, now that we only have the Euler-Lagrange equation to use, right? So we have to prove that, well, under this perturbation, the energy does not drop to the first order of epsilon. It drops to epsilon to some order that is higher than 1, and that is how we can get a contradiction. Right? So this is the part where the proof becomes a lot more technical, because when we are using the Euler-Lagrange equation, so let me just very briefly mention where the difficulty is. You might think that we are doing an order epsilon perturbation because we run this process for epsilon amount of time. Right? But actually, when you are trying to argue using the Euler-Lagrange equation, you are directly, so it is the difference between the original profile and this modified profile. It's directly this L infinity distance between them that matters. Right? So even you run it for a time epsilon, that difference might be much bigger. right? The easiest way to see it is because there's another thing that I didn't mention, that is for the steady state of this equation, because there is the degenerate diffusion term in front of it, in general, the steady state will have pretty bad regularity. So in particular, near the origin, so it may be only Holder continuous. Right, so this is a feature that is shared by all these steady states where they carry the degenerate diffusion. Okay, so for this profile, even if you think about the easiest perturbation, you just shift it to the right by distance epsilon. Okay, now if you look at the L infinity distance between the original profile and the shifted profile, the difference will be much bigger than epsilon itself. Right? It depends on what is the Holder exponent here. So for example, if this is epsilon to the, so it could be epsilon to the 1/10, something like that, right? Okay, so for that reason, when you are using the Euler-Lagrange equation, so the difference will contain a first order term that will be equal to 0, and then the higher order term, we thought it would be nice if it's epsilon square, but at the end it will be the square of this difference square. But if the difference is like epsilon to the 1/10, then squaring it, you still have some power that is less than 1, but we need that power to be bigger than 1. Okay, so this is why at the end, for these cases where we do not have rigorous gradient flow formulation, we cannot just use the perturbation like this because this L infinity difference is too bad. So to solve this issue, what we ended up doing is to use a trick to slightly modify our perturbation. Okay, because previously I'm telling you that, well, at each level we do the same thing. We use a continuous Steiner symmetrization to just shift each needle with velocity 1, right? But then at these lower places where we know the regularity is bad, there is this issue. So because we exactly know what is the regularity of the steady state. So we know that the steady state itself, the rho s itself, may have really bad regularity, but we know that rho s to the power m-1, so this thing is a Lipschitz function. Okay, so once we know this, it means it's only the lower density part whose regularity is bad. So when we are designing this symmetrization, we can manually slow down the velocity at the lower density so that so these points will be moving slower. Okay, and for that reason, we can indeed say that, well, for the new perturbation that we constructed by slowing down the velocity at the low density, that thing, indeed, if you take the L infinity distance, it's still of order epsilon. Okay, so that is how we are able to get the contradiction when m is, so if there is no rigorous gradient flow formulation. So that is the proof of the symmetry part. I think that's it for today. And for tomorrow, I'm going to continue with, once we show that all the steady states are radially decreasing up to a translation, there can still be many of them. Right? Maybe for one mass, there could be a family of steady states, always the same mass, all are radially decreasing. So we want to know whether this is possible or not. So today, what I'm discussing is just, we argue that all the steady states are radially decreasing, and tomorrow I'm going to move to the question that, are they unique or not with a given mass? And thank you.
More questions, comments? Don't be shy.
Thanks. So here you constructed rho epsilon, and I'm curious whether rho epsilon is still a stationary solution or not.
No, it's not a steady state.
It's not a steady state. Then how you can still justify that? How you can then drive the contradiction? Maybe I misunderstood something, but for me, it seems like rho epsilon need to be steady states, but why is it okay to you still claim that rho? I mean, how you can derive the contradiction then?
Oh, so the contradiction happens in the sense that if there is a rigorous gradient flow formulation, a steady state would be these densities where no matter which direction you go, you cannot be decreasing your energy to the first order. So think about this intuitive gradient flow picture, right? You have an energy functional, right? So you can only, and then so for all the solution, for all the starting point, you will be going into the direction where your energy drops the fastest, right? And you will only be happy to stay still at a point. So this will only be a steady state if for any direction you go, you are not dropping your energy to the first order, right? So in that sense, what we have constructed is a test direction, right? It's not the direction where the actual evolution in time is happening. So at this rho S, we have found this test direction such that if you are testing your solution in this rho epsilon direction, then you are dropping your energy to the first order, right? But it means that the actual gradient flow needs to be going down, needs to decrease your energy to be even faster, right, at that moment. So then you cannot stay still, right? This is not a steady state.
Thanks. Thank you very much.
More questions?
Yeah, so until the third point, you basically you study mostly the energy functional, and then you derive the contradiction using the equation only on the fourth point, right? And so I was wondering, do you know like if such a result could still hold if you take like another gradient flow than Wasserstein, that maybe h-1 or maybe even different Wasserstein metric?
So you mean
the equation?
Oh, suppose you are assuming the functional is the same, right?
Yes.
It's just the length. It's just the
flow.
metric that is different,
yes,
right?
Yes.
Yeah, I think this. Let's see. I would say it depends on whether the perturbation that you are constructing is a Lipschitz curve in that direction, right? And for Wasserstein distance, this is the case, right? Because when we are perturbing it for time epsilon, we know that because the perturbation is explicitly done by moving points like this, right? Each point moved by no more than epsilon, and therefore for the 2 Wasserstein distance or any even infinity Wasserstein distance, you know you're perturbing by no more than epsilon. Right, and that is important because a small perturbation here, if it means a big distance in the metric that you are using, then it is no longer a small perturbation, right? So in that sense, I think one needs to check whether this perturbation is the distance is less than epsilon in the metric that you're using.
Any more comments? Questions? No? Okay, so let's thank Yao again.